All right, guys, Mr. Antonucci here, and we're jumping into section 8B, chi-squared tests for independence or homogeneity. And in this first part, we're going to look at how to state the appropriate hypothesis for a test about the relationship between two categorical variables. Previously, we learned how to analyze the relationship between two categorical variables like in the snowmobile use and environmental club membership for winter visitors to Yellowstone National Park. So here's the two-way table and segmented bar graph summarizing the data from a random sample of 1,526 winter visitors to Yellowstone. Now, for both the chi-square test for independence and the chi-square test for homogeneity, I told you I'm going to say chi, I'm going to say chi. But anyway, the data for these are going to be organized in a two-way table. And the formulas and calculation for both tests are going to be identical. The difference is between the difference between the two tests is in how the data were collected, which will affect the conclusion we can make at the end of each test. So just wanted to bring that up as we get started here. And so the question, is it reasonable to say that there's an association between environmental club membership and snowmobile use in the population of all winter visitors to Yellowstone National Park? Or is it plausible there's no association between these variables in the population and association in this sample happened by chance? So here's how we would write the hypotheses for this example about winter visitors for Yellowstone National Park. The null could be there is no association between snowmobile use and environmental club membership in the population of winter visitors to Yellowstone National Park. Notice the null is basically saying there's no association, and it's in context of the problem and the association that we're looking for or not looking for. The alternative would be the same exact statement, but we say there is an association. Now, when we say there's no association between the two variables, this means that knowing the value of one variable is not going to help us in any way predict the value of another. That is, the variables are independent of one another. So another way to state this hypothesis would be snowmobile use and environmental club membership are independent of winter visitors to Yellowstone National Park. And the alternative would be stated as snowmobile use and environmental club membership are not independent in blah, 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 and so forth and so on. So notice these are two ways to state the same null and alternative hypothesis, or to state the null and alternative hypothesis for the same situation. All right, so a tip here is many students are going to lose credit on the APA Stats exam because they reverse the null and alternative hypothesis in a test about relationship between two categorical variables. So remember that the null hypothesis is the dull hypothesis. That is, there is no association between the two variables. Okay, so just be careful there that you don't reverse the two. So here's an example. Pew Research asked 500 randomly selected U.S. adults about the proportion of their extended family members who live nearby. Nearby was defined within an hour's drive, and the response options included all or most, some, only a few, and none. Extended family was defined as children, parents, grandparents, grandchildren, brothers, sisters, cousins, aunts, uncles, and in-laws. Respondents were also classified by the region of the country they live in. So, is there convincing evidence of an association between region of the country and proportion of extended family for U.S. adults? Here's a two-way table. We have the two variables, proportion of extended family nearby and region. And here's a two-way table, the results with the row totals and the column totals. So we want to state the appropriate hypothesis for a test about the relationship between region of the country and proportion of extended family nearby. So here's how we would state this. The null would be there is no association between region of the country and proportion of extended family nearby in the population of U.S. adults. The alternative, same exact statement, except we'd say there is an association between region and extended family. So you could also state the hypothesis as the region or the null is region of country and proportion of extended family nearby are independent in the population of US adults. And the alternative would be same exact statement, but saying not independent. All right. Now we want to calculate the proportions in each region who responded none. So how we do this is you have to look at each region. So there's Northeast, South, Midwest, West, and the amount in each is 13, 45, 21, 28. But to calculate the proportion in each region who responded none, so the Northeast is 13 out of 84. 13 out of the 84 in the Northeast region responded none. Okay, so we're looking at the proportions within each region. So the South, Midwest, and West were the four regions. Notice you're doing that cell amount divided by that column total right here. So those are the proportion in each region. Now, notice there is a difference in these proportions. So explain how our answer to part B gives some evidence for the alternative hypothesis. Well, there is some evidence for the alternative because the proportion of people with no extended family nearby isn't the same in each region. So this is basically like saying knowing a person's region of the country helps predict if the person has extended family nearby. Now, people who live in the South and West, South and West, are more likely to have no extended family nearby just because those proportions in our sample were higher. Okay, so now we want to look at the next piece of this, which is how to calculate expected counts for a test about the relationship between two categorical variables. So when we assume the null is true, the expected count for any cell in a two-way table is going to be the row total times the column total divided by the table total. Now, the formula for the expected counts is not going to be given on your formula sheet. So this is why, another reason why it's important to understand why the expected counts are calculated this way. Again, row total times column total divided by table total. Here's our example. We have the two-way table summarizing the relationship between region of country and proportion of extended family who live nearby for a random sample of 500 adults. Now we want to calculate the expected counts for a test of the null hypothesis. So here is that table of values again. And remember that to get the expected count, you take the row total times the column total divided by the table total. So if I want Northeast 13, I would have to do the row total times the column total, so 107 times 84, divided by the table total, which is 500. So here's what all of the expected counts would look like. One thing that's important is you're not going to do the expected counts for the totals in this, just for the table values, okay? Also, you're not going to want to round the values to an integer. Go out at least one, two, or more decimal places if you need to. Okay, so for this, here is our entire table calculating or with the expected counts for them there. All right. Another tip is you have to report the expected counts when checking the conditions on a free response question, and you're not going to get credit for a statement like all expected counts are greater than or equal to 5 without showing the values of the expected counts. So when you're given a two-way table of observed counts, you can record the expected counts in parentheses directly near or directly next to or below the observed values in the two-way table, as long as you indicate somewhere that the values in the parentheses are the expected counts. So you have to literally show that the expected counts are all greater than 5. So, with that being said, we're now going to talk about checking the conditions for a test about a relationship between two categorical variables. So, as with the chi-square test for goodness of fit, we need to check the random 10% and large count condition before we perform a test. This is going to help us know that the data is independent in its collection process and that the chi-square distribution will be a good model for the sampling distribution of the test statistic. The conditions are exactly the same as the test for goodness of fit. So we have the random, the data come from a random sample of population of interest, 10% when sampling without replacement, the sample size is less than 10% of the population, and the large count condition would be that all expected counts are at least 5. So let's go ahead and jump into an example here. So if we think about this problem with the 500 randomly selected US adults, about the proportion of their extended family that live nearby, I'm not going to go over all of that context again, but we want to check if the conditions are met for performing a test about the relationship between region of country and proportion of extended family. So we want to check the random condition, just a random sample of 500 US adults. That's sufficient. But you don't say random and then put a check mark. You have to have at least a sentence there explaining that the sample was a random sample. 10%. Well, it makes sense that 500 is less than 10% of all US adults. And the large counts. We had calculated the large counts up here in this table. So if we do that, we can actually refer to that as we're working through the problem. So all expected counts, and then we listed them, are at least 5. So make sure you reference the values of the expected counts when checking the large count condition. Okay, it's essential that you do that, that all the expected counts. You don't want to say all the counts, and you certainly don't want to say all the observed counts. You want to specify that it is expected counts. All right, guys, that's it for this video. Hope that was helpful. Reach out if you have any questions. Take care.